First of all, of course, I'd like to thank the organizers of this beautiful conference. Korea is great, so thank you very much. The title is very long, and in fact, I'll be speaking about equivariant embeddings. And this is a joint work with Viktor Matveyevich Buchstaber from Steklov Institute, who you know very well. Well, the main object is a quasitoric manifold M, determined by combinatorial data. And I will give all definitions below, and we'll be following the paper by Buchstaber, Panov, and Andrei from year 2007 throughout this talk. And the notion itself was given in 1991 by Davis and Urkevich. In short, we'll be utilizing construction of M as a quotient orbit space of smooth ZP by K. But again, I won't stop here, since I'll give all definitions. Well, we're starting from simple N polytope, defined by inequalities of this type. There are no redundant inequalities. There are exactly M of them. And the simple polytope is just a polytope in generic position. Every vertex is intersection of exactly N facets. So here is the matrix form. And you can see that we naturally have the affine map from Rn to Rm. And under this map, the image of P may be identified with the intersection of affine image with a positive cone. Well, so far we have another map to the positive cone. We have a map from CM to positive cone. That's the standard moment map. And so we have the following commutative diagram. And we may now define a moment angle manifold as a pullback in the following diagram. Well, it's simply the preimage of P under the map ρ. And clearly this is a set. This is a compact set, since ρ is a proper map. But what can we say about ZP? What more can we say about ZP? Well, then there is a theorem, Buchstaber, Panov, and Andrei, that the manifold ZP is in fact a manifold, and its intersection of the following quadratic equations, hypersurfaces. Well, you can see them here, and the equations are very simple in fact, and it turns out that ZP is a manifold in a singular intersection. Dimension is M plus N. It is smooth, it's real algebraic, and finally it carries an action of compact torus Tm. Well, that's great. We have a canonic smooth structure on ZP under this approach, and that's very convenient. And some more definitions. We will say that sequence of indices I is admissible if the corresponding intersection is not empty in P. If we have the sequence I, then the corresponding face is Fi, and we denote by Ti the following toric subgroup, the product of corresponding subgroups. And to define quasitoric manifold itself, we need some more information. In fact, we need a homomorphism lambda that satisfies independency condition, that if I is admissible and if Fi is a face, then lambda is required to be a monomorphism on Ti. Well, that's actually a very strong condition. Not every combinatorial polytope P admits a characteristic function, and that's more of a theory of Buchstaber number, and we won't stop here. We'll just suppose that we have a polytope P with, say, some characteristic function. And in particular, when I is admissible sequence of length n, then Ti is an n-dimensional torus, and lambda is required to be an isomorphism. So lambda is necessary a map onto. And lambda is in fact a combinatorial object. We have an integer matrix such that it's determined by integer matrix such that if V is a vertex, then we can form an integer matrix, square integer matrix, and the isomorphism condition is equivalent to the fact that determinant is plus minus 1. And we can consider now the short exact sequence generated by homomorphism lambda, where K is a subgroup isomorphic to torus Tm minus n. And you can verify that by construction K acts freely on manifolds ZP, and we can now define a quotient space. This is smooth, this is compact space. We call it a quasitoric manifold associated with combinatorial data P lambda. Recall that it again has a canonical smooth structure, and throughout the talk we'll be working with this representation of quasitoric manifold. Denote by P the corresponding projection map. We'll need it later. So far we have defined quasitoric manifolds. We have described smooth structure on it, and to speak a bit more, what's the motivation for definition? Well, you also clearly know that. The motivation is that any projective non-singular toric variety has in fact the structure of quasitoric manifold because the action of compact torus is Hamiltonian. And in this case we have a natural moment map, and it's well known by Atiyah-Gemin-Steinberg theorem that simple polytope P is an image of this map. So we have the polytope P, and the matrix lambda is given by the set of one-dimensional cones of the corresponding fan. And in order to proceed, we'll describe the isotropy subgroups of torus action on M, and that will be enough for definitions. Well, we have the natural characteristic function denoted by He that puts in correspondence to point X the isotropy subgroup of X. It's very simple. And in our case, since torus is an abelian group, He is well defined on orbit space, not just on M. And moreover, if F circle is the interior of face F, then we can give an explicit answer. He is constant on each open face, Fi circle, and He is equal to subgroup lambda of Ti. This is exactly the role of lambda in our setting. Lambda is a homomorphism that describes the isotropy subgroups on our quasitoric manifold. And what will be of particular interest for us? Well, in this talk we'll be considering the set of pairwise distinct codimension 1 isotropy subgroups. Well, clearly each subgroup of isotropy subgroup of dimension n-1 corresponds to some h, but the number q of distinct codimension 1's isotropy subgroups clearly does not exceed of number of edges, but it can be significantly smaller. It's obvious for, say, cubes or products of polytopes, but not only for them. And we'll have an example of Stasheff polytope. And well, each subgroup HI determines a homomorphism. Once a thickened orientation in quotient group Tn by HI, and clearly this homomorphism is determined by an n vector. And we will consider a, say, composite representation from torus Tn to torus Tq. This is a large representation, large matrix, denoted by W. So it's n times q, where n is our dimension, q is number of, say, all isotropy subgroups of codimension 1, and q is bounded by number of edges. And the result is that phi generates, I'll explain what the word generates means an equivariant embedding of M to linear Euclidean space Rn times Cq. Rn times Cq is a relatively small dimension for this type.
Can you back down one more slide to see what fields?
This one, yeah? We have quotient.
The definition of phi?
Yeah, what is the definition
Of Q? Well, I think I was too fast. The Q is the number of these isotropy subgroups of codimension 1. Well, we have edges of polytope P, and each edge has an isotropy subgroup. Some of them are equal. And then we just denote by Q the number of distinct subgroups. And And from the other side we have the quotient representation, which is epimorphism here, and there are q of them. So we just take the direct product of them. This is definition of phi large. So this is a very natural object, but the point is that it is of some use of us. It can generate equivariant embedding. Let me describe how. Well, what do we know about embeddings in general? We know that by Whitney theorem, any compact closed manifold can be embedded into R2n. And moreover, there is a well-developed theory of embeddings based on Hirsch lemma, characteristic classes. We can have sharp bounds in many different cases. And what is known in equivariant case? In fact, equivariant case is the moment where I'd like to ask you what is in fact known, because there is an existence theorem, named Mostow-Pale theorem,
that's Pale, not P.
Pale.
Pale.
I have to put an accent, yeah? I had to put an accent.
Yes.
Yes, I see. Yes, I'm very poor in languages. It's my only. That's a bit of Deutsch. Any compact manifold M with smooth action of Lie group G, in fact, may be embedded into the space of linear representation of G. But that's purely an existence theorem. The proof is very ineffective in terms of dimension. So the problem is, how can one estimate the dimension of current embedding? So my question is to know whether there are some classes of smooth manifolds, of algebraic smooth manifolds, for which an estimate of embedding dimension is known. I don't know. This talk is about quasitoric manifolds and therefore projective toric varieties. We can have an equivariant embedding for them, but I don't know what else is known. So how are we going to do that? Well, our main ingredient are monomial maps defined by Cm, taking values in C, and they're very simple. Each integer vector of length m determines a real algebraic map by the following simple formula. We just take an ordinary Laurent polynomial, Laurent monomial, but clearly it's not defined everywhere, and we want a smooth map, so we just replace all negative powers with positive powers of z bars, of z bars. Is it clear? Okay. Proceed further. This is a simple object, and the first obvious lemma is that monomial map restricted on our moment angle manifold vectors through quasitoric manifold if and only if A is a linear combination of rows of lambda. And you already know what are we going to perform now. We'll take lots of monomial maps of this kind and show that somehow the distinguished points of ZP, and you're right, will denote by phi m from moment angle manifold ZP to CQ the smooth map generated by columns of this matrix. We have matrix lambda, that's combinatorial data, transpose it, and multiply by W, and we get exactly matrix of the form m times q. And it generates equivariant embedding wrong. It does not. If you have a CP1, then q is equal to 1, and we can't embed two-dimensional sphere in C. We have to take something else. And recall that we also have a projection map from moment angle manifold to P, and clearly it also factors through M. And the theorem is that the product map rho P times phi m defined on ZP and taking values into product of polytope P and CQ induces certain equivariant embedding of M corresponding to linear representation that is trivial on first summand. We assume that Tn acts trivially on P. And the representation CQ is obviously phi, determined before. Well, here's a short sketch of the proof. We don't use Mostow-Pale theorem because we have an explicit explanation of our manifold in combinatorial data. We construct a large equivariant monomial map that is indexed by all faces of P, not only by edges. And the space of embedding, you can see, is very, very large. But sure, in this case, it's possible to show that it distinguishes points of M. And the second point is that it turns out that the complicated map tilde Phi can be replaced by small map Phi, that is, components corresponding to edges are enough to generate another components of this map. I won't go in much detail here, but I can explain after talk, of course, since I don't have enough time now. Once the scheme is given, it's not very, once the tilde Phi is constructed, it's not very hard to show that it really distinguishes points. Rho P times Phi distinguish points. So I can explain how it is done later. Okay, this is the scheme of the proof. Sketch of the proof. And here are the simplest examples. Well, what's the simplest toric variety we know? This is P is a segment, M is CP1. Z moment angle manifold is three-dimensional sphere. And we have n equal to 1, q equal to 1. And the map is given by this simple formula. The complex part is Z1, Z2 bar. And CP1 may be embedded into R3. That's not a surprise. We all know that embedding. And but it's actually important because it shows that our construction may not be blown down. This is sometimes our dimension estimate is sharp, at least for CP1. I don't know for general cases, but at least here. Well, let's take the projective plane. That P is S5. The group K is again a diagonal subgroup, so this is simpler. But the matrices are more complicated. Here are them. Lambda is, the columns of lambda are one-dimensional cones. W, the columns of W are weight vectors of torus T2 acting on holomorphic curves in this case. You can see the weights, they can be chosen as follows. And here's the product, and lambda transpose 2V W generates monomials of this form. Okay, there is another description. Viktor Matveyevich insisted me to include it here. And for CP2, there is another strange way to obtain these monomials. We can multiply Z transposed by Z bar, and obtain a matrix whose upper triangular part generate our embedding. So, since sum of squares is 1, the embedding space is R2 times C3 equal to R8. So the result is that CP2 can be T2 equivariantly embedded into the space R8, Euclidean space. Don't know whether it's new, but the fact itself is funny. And here is another example, a bit more complicated, but actually very important. Maybe you remember the sketch of the proof. There were two steps. First of all, there was some large map to some large space, and then it followed that we could reduce the number of monomials. And we had actually to consider the example of Stasheff polytope to indeed show that it is possible to decrease the number of monomials. Here is the polytope. Here is the matrix of one-dimensional cones of our fan. And if we enumerate facets as in this matrix, then every edge is formed by these pairs. And here are the components of monomial map. Well, include here just to show how complicated it can get in case of, I don't know, Stasheff polytope. Not very hard, not very simple. Stasheff polytope gives us an example that Q is 6, but the total number of edges is 21. And maybe you already see that the number of distinct isotropic subgroups in case of projective toric variety is actually number of edges up to parallel edges. So you can see that, let me show you Stasheff polytope. There are 21 edges here, but only, as far as I understand, only 6 edges that generate maximum non-parallel set. In case of toric varieties, the weight vector is the edge itself. So we just combine non-parallel edges here, and they generate an equivariant embedding. So the Stasheff polytope is an example of two-truncated cube. The theory of these polytopes has been developed by Mostow-Pale and Volodin. The paper is of year 20 and 12. And actually, the theory of pairs p lambda is very simple for this class of polytopes. Namely, when you truncate to truncated cube, then the corresponding normal vector is the sum of two normals to the facets being truncated. So we can describe the pairs p lambda for this class very simply. And moreover, two truncated cubes include many other classes of polytopes. So the problem is, how can one estimate value of Q in terms of sequence of two truncations of cube in this class? Well, clearly Q is a number of non-parallel edges for projective toric varieties. But if we have a general quasitoric manifold, then lambda may be very different from the set of one-dimensional cones. And it follows that Q will be also different. So this is not clear in general case. And the last thing I'd like to tell you about is actually that we may define the signs of fixed points of quasitoric manifold in terms of our equivariant embedding. Let X be a fixed point of torus section, and Px and the projection of X is a vertex V. Then we may denote by CV the space corresponding to n isotropy subgroups of edges starting in vertex V. And it's worth to note that CV is indeed of dimension n, that is, edges meeting in vertex V are indeed linearly independent. The representations are different. And we have a natural map that is differential from Tx of M to our space and to CV. That's the map, that's the linear map of real to n-dimension spaces. And also we'll need the matrix SV, that is product of these two matrices. That's pairing of matrix lambda V of that submatrix of our combinatorial data. And the matrix of weights. And SV is actually a very simple matrix. It's not written here, but SV is a unit matrix with some rows transposed and some plus ones changed to minus ones. So SV is a, say, correction matrix for our degrees of freedom. And the theorem is that the sign of product of these determinants equals to sign of fixed point, defined as in paper of Buchstaber, Panov, and Andrei. And the sign of fixed points is was in fact a very important notion. It's always +1 for projective toric varieties. But for quasitoric manifolds, it's not necessary +1, and it controls lots of important stuff, such as stable complex structures or cobordism classes. And it follows that we can define the signs of fixed points in terms of equivariant embedding. And it's possible to reformulate the result on invariant almost complex structures only in terms of equivariant embedding. The result was that a quasitoric manifold M admits a T-n invariant almost complex structure if and only if all signs of all its fixed points, as defined in theorem 2, are positive. This is not a new result, but now we can give another criteria for existence in terms of our equivariant embeddings. And maybe that shows that these two problems are somehow connected, this is the strongest way. We could relate them, but maybe you'll be more lucky. So, hence the criteria may be reformulated in terms of our embedding. You already heard that. And, if I have a time left, and surely I have. And then speaking of, then speaking about invariant almost complex structure, we have a natural inclusion that from CP1 to R times C and to C times C, but clearly our equivariant embedding does not respect invariant almost complex structure, since there are no holomorphic embeddings of compact complex varieties into affine spaces. We can see it very simply using characteristic classes, since the Chern class of normal bundle should be trivial, Chern class of affine space is trivial, and if such embedding exists, we should have Chern class of tau CP1 should be trivial, but that's not true, since Chern class C1 of CP1 is equal to Euler class and is equal to 2. Well, maybe that was too fast. Let me thank you for the talk.